Okay, guys. Sorry that I'm not in. So I kind of wanted to put this together. Uh, it's about an hour and a half before you watch this. Um, so if you hear somebody else, it's my son because he has the flu and I'm home taking care of him. So hopefully he won't come in. Um, so last class you was working on internal energy. This is all thermodynamics. In thermodynamics, in this book, is this is the online book or the book itself. It's broken up into two sections. This section, which is what they call thermochemistry, and then chapter like 16, which is the rest of thermodynamics, which is the study of the flow of energy. There are three laws which we'll talk about later, but the big thing about the when you do thermodynamics, and I'm going to scroll down a little, is you should have already read this. Um, that when you do, there's something called heat and work, uh, and you looked at internal energy. With thermodynamics, the properties are what I call state functions or state properties, which means it's not pathway dependent. It's where you start and where you finish and that's it. So you look at the start and the finish. That's it. Um, the other big thing is that you always create what is called a system. A system is the thing that's going through the change, and everything else around it, everywhere, is the surroundings. And you add up the system and the surroundings, and you get the universe. So there's always three things: the universe, the system, and the surroundings. And the reason why that's important is because the flow of energy works both ways. And why that is important is to equate the physicalness of the energy movement into mathematics. Signs are important. Signs tell you how the energy is flowing. Okay? And that's why you create a system and a surrounding. And depending on what you're talking about, a positive, let's say, positive something could be the system giving energy to the surroundings, and the negative could be the surrounding giving the energy to the system. It all depends on the physical property. That's why it's really important to set up the system. And again, the system is just the thing that's going through the change. Um, so so you learned about that, and then okay, you talked about the first law, the internal energy, and they have heat in work, the two types of energies. So you did all that. You can do all that. Now the next thing is you start off with your second state function. The first state function is internal energy. The second state function, which is the more common one, is down here, called enthalpy. And basically what enthalpy is, and they go through the mathematical derivation and the physicalness of it, but here, right here, after you do all these things, what you get is you get delta H, which is the enthalpy change, and it's always final minus initial is a delta in thermodynamics. Final minus initial. So your change in enthalpy is equal to the heat flow. So there's a stipulation that says it has to be a constant pressure. But most everything you do is at constant pressure because we live in an environment, and that's a constant pressure environment. So it's almost a given that happens. So that's why enthalpy is a really important topic, and that's why it's the first thing they teach you for state function. So basically the rest of the chapter is all about how you calculate enthalpy, which is delta H. Again, it's a state function, it's a thermodynamic function, so it's always delta H is equal to the enthalpy of the products minus the enthalpy of the reactants, if it's a reaction, or the enthalpy of the final condition minus the enthalpy of the initial condition. So, with that being said, that's heat. So that's how you calculate heat flow. In general, heat flow is, if it's a negative delta H, it means the system is releasing energy to the surrounding. If it's a positive delta H, it's the surrounding giving energy, or the better way of saying it is that the system is absorbing energy from the surrounding. So that's what it is. So now, sorry, I went way too fast. So now what happens is simply, and I'll get back to where I was. So now what happens is, that's what these two things are. Now what happens is, now you just you're calculating delta H, and it's both a chemical thing and a physical thing. So there's basically 3 ways in which you can calculate delta H. One is by calorimetry. So that's what this is. Okay, calorimetry, which is basically another way of saying, using water, you can determine the heat flow of a substance if you surround it with water and check the temperature change of that water. And it's important, as long as you don't go through a phase change, because phase changes have different equations for the heat calculations. So there's a billion different names for these conversion factor constants. Here's heat capacity is one of it. There's specific heat capacity, molar heat capacity. All it is are units that you have that will make the units of the mathematical relationship work. These constants are specific to the substance that's going through the change. It's very important to know what is going through the change. Okay, that's why most of the times when you do this, not only do you have constants like unit symbols, you have underneath the symbols you have the material chemical formula or some notation of what that substance is. So here's a calorimetry. It's basically a styrofoam cup. Okay, you I mean, maybe did this in first year. You put energy in, you heat the cup up, you figure out how much energy you put in. You can do all kinds of things. You can heat up a cylinder, dump it into water, watch the water rise, figure out how much energy is being released by the cylinder, by how much is gained by the water. That's how you figure out the calories in your food. So that's one way. Yeah, there's a constant pressure one, which changes the equation, which we'll kind of hold off on right now. Okay. Next type of calculation is called Hess's law. Since enthalpy is a state function, which means it's the starting point or the finishing point in the difference, what Hess's law basically says is that if you want to be able to know I'll use height, the height difference, you can measure the height in one shot, or you can measure it by taking like blocks and putting blocks in that equals the same height, and if you know the block heights and add them up, you have the height that you want. In essence, it's you can build your chemical delta H for the chemical reaction from other chemical reactions. Okay, and Hess's law, there's a good example on here. The big thing is when you flip an equation, change the direction of the equation, make the reactions to products reactions, the delta H sign flips. If you send through a 2, coefficients 2, your delta H doubles, or halves, and all that stuff. And then what you do is you simply build it, add them, and you get the chemical reaction that you want, and therefore you have your delta H of that new reaction. It's kind of like making a puzzle, and the pieces are the chemical reaction, and each piece has a value, which is the delta H. And the book does a really good job of explaining it. And then the last one. Okay, so that's the second way. Okay, and the last one, and these are you'll see the Hess's law, the fact that you can make the chemical reactions for state functions equal basically algebraic manipulations. That's basically what you're doing. Okay, that's common to all the thermodynamic properties, not just delta H, as we'll see. The last one is building it from scratch, which is called the standard enthalpies of formation. And what happens here is the difference, since all state functions are final minus initial, so you're creating and figuring out a difference. No differences have any value at all until you create something that's the starting point. So, for example, my house is 1 acre. Well, that's all well and good, but where's that 1 acre I live in Pembroke. Where's it in Pembroke? Well, there's actually, before GPS, there's actually something that there's a place, it's called a benchmark, it's on the street usually, that's the point where surveyors take to figure out my acre of land, or whatever it is, quarter acre, whatever, where it's located in the universe. Because an acre is an acre, or half an acre, but it doesn't show you where. So you need something to nail down the difference to mean actual numbers. And that's what the standard enthalpies of formation do. What they basically do is every substance you can make energy-wise from its elemental form. The elemental form of of anything has an energy value, enthalpy value of 0. And then you build each compound. And when you build it, it's going to require energy or it's going to release energy. So for that substance, you have a delta H of formation. Well, all chemical reactions are a bunch of different substances. So what you then do is you then use the coefficient in the front, because that tells you how many of the particles there are, and then you just add all of the reactants together, get the total energy enthalpy of the reactants and the total enthalpies of the products, and you subtract them. But since it's thermodynamics, it's always final, which is the products, minus the reactants. And when you sum them all up, all the reactants, in this case, all the products together, and all the enthalpies of formation times the coefficient in front, because all these enthalpies of formation is for 1 mole of one substance. And the coefficient tells you how many moles you have. And you add them all up, you get the total enthalpy of formation for the products, subtract it from the total enthalpy of the reactants, and you get the delta H of the reaction. And those things are all those standard heats of formations for each of the substances. They're in the back of the book because they're already known. And you can read it again. These guys do a pretty good job of explaining it and also going through it. So give them a try. Give each one a try, or as much as you can. And then when I'm there on Monday, we can go through it. So I'm going to just give you one problem from each of the different types for you to do, and these are all calculating delta H's. Okay. So again, I hope this helps a little, and hopefully I can get this little explanation to you in time. Okay. I'll see you on Monday. Bye.